When ions cross the membrane, it creates a current. Why? Because a current is a movement of charges. Since ions are charged particles, their movement creates a current. A current equals Q over T. Q is the quantity of charges passing through a channel, and T is per unit of time. The current and the voltage are related by Ohm's law. And it says, in the case of a membrane, that the voltage across the membrane is proportional to the current through it. Here you have the voltage, and here the current. We have seen the potential, which is the membrane potential. We have seen the current, which is the ion currents, and the resistance we have not seen yet. It is the resistance of ions to move through the membrane. They do not move very easily. There is resistance to their movement. Through a single channel, the Ohm's law writes like this: Vm, which is membrane potential, minus E ion, which is the equilibrium potential of the ion. Rho here is called driving force. It's the driving force due to the electrochemical gradient. We have seen that when Vm equals E ion, at the equilibrium potential, there is no net movement of charges. So to get a movement of charges, the potential must be different from the equilibrium potential of the ions. And equals, here we have the Ohm's law, R multiplied by I of ion. R is the channel resistance. Here we speak about a single channel. So it's the channel resistance. And I ion, it's the unitary ion current. It's written with a lowercase I. Here is Ohm's law again, and we will transform it because in neurons we like to calculate the current. So we will introduce a new variable called gamma. R equals 1 over gamma. Gamma is the inverse of the resistance. It's called the conductance. The unitary conductance here, it's expressed in Siemens. I remind you that the driving force is expressed in volts, the current in amperes, and the resistance in ohms. The symbol is omega. And here, conductance is in Siemens. So now the Ohm's law is expressed like this, and it goes to the current through a single channel equals the conductance of the channels multiplied by the driving force through the channel. Through a single channel, we have seen how to write Ohm's law. What happens now when all the channels of the membrane are open? We have what we call a total current. It's capital I of the ion equal G multiplied by the driving force. And the relation between single channel current and total current is this one. What is NPO? NPO is the N is the number of channels expressed in the membrane, and PO is their probability of opening. So NPO is the number of open channels at the time of current measurement. So we understand here that the unitary current is multiplied by the number of open channels, and it gives the total current. And it's the same for the conductance. What is the role of ion currents? The primary function of ion currents is to change membrane potential. For example, if potassium ions exit the neuron, the membrane potential will become hyperpolarized because the inner side of the membrane will lose ions that are positively charged. If ions with a negative charge enter, then the membrane potential will also hyperpolarize. If ions with a positive charge enter, then the membrane potential will depolarize. And these changes in polarity, depolarization, hyperpolarization, are neurons' typical signals. We will see a very important signal referred to as action potential in Chapter 2. But ion currents have also other functions. By depolarizing and hyperpolarizing the membrane, they can open or close other channels that are sensitive to voltage changes. And finally, The currents can change the concentration of an ion very locally and transiently. And we will see one example like that for calcium ions in chapter 3.